So, yesterday we did a lot. We learned about Bott-Samuelson bimodules and Zergel bimodules and about, a bunch of polynomials and a bunch of various slots. We learned about them in sort of a very concrete algebraic way. And now we're going to learn about them from an entirely different angle. Okay? We're going to sort of ignore the fact that these things that we care about are bimodules with this presentation by putting polynomials in certain slots, and studies only the morphisms between these bimodules. And we're going to take these morphisms and represent them diagrammatically. Now, why would we do this? I mean, I may have said it a couple times, as an example, for instance, when m is 4, we know that this thing right here is supposed to have as a summand this thing R tensor over R ST R with the shift by 4, which is also supposed to be a summand inside, say, BT, BS, BT, BS. And so, for instance, there should be some morphism, from here to here, which is project to the summand and include back there. Okay? Now, one should be able to write down this morphism explicitly. It sends this, this is 5 polynomials with 4 walls. Send these 5 polynomials to some linear combination of 5 polynomials over there. Write this down explicitly. This is a real giant pain. It's very hard. There's no nice closed formula that as far as I know. And it's just this is the reason we didn't prove these facts yet. It's because these formulas are very hard. And suppose that we then take this morphism and compose it with a bunch of other morphisms. Now you're really in trouble. Okay? But what we're going to end up doing is we're going to take this morphism and we're going to abstract it into a picture. Actually, the picture is going to look like this. I'll break out the colors in a sec. That's what the picture is going to look like. And when we abstract this morphism into a picture and we figure out the rules for manipulating pictures, it will be easy to compose these things. Okay? And you'll be able to actually do math. And you'll be able to prove facts like this sort of directly using the morphisms and never even talking about the polynomials that went into it. Right? This is the goal of today's talk, is to introduce diagrammatics and get used to how they work. Okay? There's another statement, which is more of an abstract one, which is that we're dealing with a monoidal category. And it's a monoidal category with biadjunction. Okay, so remember that tensoring with BS is left and right adjoint to itself. And whenever you have this situation, the correct tool for studying morphisms is diagrammatics. This is just a general statement, a general phenomenon. You'll kind of see a bit of why today. Okay, so it's so planar diagrammatics. I'll be more precise, and I'll be more precise later. Is the right tool. Okay, and which is why we're going to use it. And I guess the final thing to say is that really planar diagrammatics is not just for monoidal categories. It's for 2 categories, whatever 2 categories are. But a monoidal category is just a 2 category with 1 object. So I'm going to talk about 2 categories for a little while. Keep in mind, I'm really just talking about monoidal categories. All right. Actually, first I'm going to talk about 1 categories. Categories, like we know and love. Okay, so linear diagrams for 1 categories. So this is just sort of a warm-up to get you in the mode. Okay? So 1 categories we're familiar with. And in a 1 category, you might have an object M, and an object N, and maybe a map F. And then we might compose that with a map G to another object P. You'll note that my arrows go from right to left. This is not because I'm a jerk, because this is how composition writes, right? This composition is G composed of F, right? All right, so this is just, unfortunately, we should have all gotten used to drawing our arrows to the left, but only in, I guess, Hebrew and a couple other languages are they smart enough to do that.
Is there anything else? I thought Hebrew was the
Yeah, okay. Yeah, I mean, there's a lot of languages related to that. Isn't Arabic? No?
Arabic.
Yeah. Okay. So what we're going to do to take a diagrammatic version is we're going to take the dual picture to this, right? M looked like kind of like a point, and this morphism was a line segment. So I'm actually going to turn M into this line segment, and then F into a point. Okay? So this is the same data, it's just another way of writing it down. Okay? It's going to be a slightly nicer way of writing it down. Now, what's the difference between this way of drawing it and this way of drawing it? This way kind of has some sort of positional data. Like, where are the points? Where did I put them? Right? But I mean, we could have done this here. It just that nobody draws things like this. Okay? And the reason that nobody draws anything like this is because of associativity. It doesn't matter what order you compose morphisms in. It doesn't matter sort of like, you could have maybe used, say, if we're trying to figure out what order to compose morphisms in, do the short ones first and then the longer ones or something. That would be a reason to have positioning. But associativity says it doesn't matter. It's just a bunch of points in a row. We just care what order we compose them in. We don't care how we specifically do it. So positional information is irrelevant. Okay? That's the point. So associativity says that. So let me just describe how this picture works. And then I'll get back to that point. So in a picture, a generic point is an object. So if I just chose a point at random here, that's N, that's M, that's P. Okay? And I'm not choosing that point. Okay? And so a generic, but I'm going to stop writing this down, interval is a morphism from the right endpoint to the left endpoint. Okay, so for instance, this interval right here is the morphism F from the right endpoint M to the left endpoint N. This interval here is the composition of F with G. Okay? And this interval here is a map from N to N. What is it? It's the identity map. Nothing's happening in there. Okay? So the identity of an object is just this boring interval when nothing happens. And composition of two morphisms is horizontal concatenation. F here and you have G there, and you stack them next to each other. That's composition. Okay? Nothingness clearly concatenates correctly. Okay? So we have this particular diagrammatic way of saying it, and the axioms of a category, well, there aren't many axioms. There's really just the existence of identities and associativity. So associativity says that a diagram unambiguously represents a morphism up to linear isotopy. So in other words, we're allowed to move these points right and left. We're allowed to move the points around, but they don't cross each other. That's not allowed, okay? So we're allowed to do anything like that. And associativity says that whatever you do, it doesn't matter. Such a diagram represents a morphism. An isotopy class of diagram represents a morphism. So this is all pretty trivial. But it's just getting used to this language. So now we're going to do the exact same thing. Instead of linear diagrams for one category, we're going to do planar diagrams for two categories. So again, you have the old way, which is, what's my favorite two category? The two category of categories. Okay, so maybe you have a category here, or it's called an object in a two category. And you've got another one there. And then maybe you have a one morphism and another one morphism. Or, you can think a functor and another functor. And between these things, there might be a two morphism or a natural transformation. Okay? And we draw the situation like this. All right, well, now we're going to dualize this picture. Okay, so instead of C being sort of a point and G being a line and alpha being a cell, we just dualize. C is represented by a region, D is a region, F is sort of a line separating this region, G is another line separating these regions, and alpha here is a point. Okay. So again, what's the convention, right? So a generic point is now an object. Okay, so if I just choose an arbitrary point, boom, there it is. That's C. Okay. A generic horizontal line segment is a one morphism. So if I chose this horizontal line segment right there, that's the one morphism F from the right endpoint to the left endpoint. Okay? And this is the identity one morphism of C, with the same exact rules as this whole set. Okay? But now a generic rectangle is a two-morphism. And again, you know, I chose that things went from right to left. I'm also going to choose things go from bottom to top. So from the bottom line segment to the top. Okay? So this rectangle right here represents the two-morphism alpha going from the bottom segment, which was the one morphism F, to the top segment, which is the one morphism G. Okay? Now, why does one use rectangles and planar things? Because there's two ways of composing morphisms in a two-category. You can stack them on top of each other, which is the usual composition of two morphisms, or you can stack them side to side, which is sort of the tensor product or the monoidal structure, the horizontal composition. Okay? So, you know, to give you another example, for instance, here's a situation you might have. Here's C. I'm going to draw this and start labeling it. You've got three objects. You've got a whole bunch of one morphisms. And you've got a pair of two morphisms. So in this picture, what has just happened, right? There is some one morphism F from C to G. There is some two morphism alpha from F to G. And there's some other two morphism beta from H to J. Okay, and what we've done is we've first taken alpha and composed it horizontally with the identity map of H. Then up here, we've taken beta and composed it horizontally with the identity map of G. And then we've stacked these two things vertically. Okay? That's what we've just done. On the other hand, we sort of know, you know, that if we take the tensor product of two maps, they commute, right? It doesn't matter whether you do F tensor 1 and then 1 tensor G, or 1 tensor G and then F tensor 1. Those are both the same map, so that this is supposed to be equal to the same picture, except with beta happening first and then alpha. Okay? So you know that we have this sort of rectilinear isotopy. We moved things around. We didn't slam any lines into each other, but we moved them up and down and right and left relative to each other. And so this is both an example as well as an axiom in a two-category. This is one of the axioms in a two-category. Here's another axiom in a two-category. Yeah, you only ever want to glue rectangles horizontally or vertically. So you know you want to take this diagram and sort of decompose it into rectangles that all meet each other, like, you know, in these kind of ways. But you don't want to decompose it into, you know, this and this. That doesn't make sense.
So only rectangles you can compose are roughly stacked correctly.
Yes. Yes. That's right. So here's another circumstance you might have. Okay. There's only one region. It's all labeled C. Here's F, and here's G. Here's alpha, and here's beta. So what is this diagram? Okay? Alpha is some map from what? Okay? Well, it's some map from the identity one morphism of C to G. Okay, so this is a map from the identity one morphism of C to G. This is what alpha does. Okay, or two morphism. Okay, and this is some two morphism from F to the identity one morphism of C. And the claim, one of the axioms of a two category, is that we can sort of slide these around. Beta alpha. So here's another thing you could do, right? So this, you split this into rectangles, right? This is alpha composed of the identity of B, and then you do that thing composed of the identity of alpha, of G. Whereas in this one, you just sort of compose them in a more direct way. And these are supposed to be equal. That's another axiom of a two category. But what you should visualize is that what you're doing is you're taking these strands and just moving them up and down. Okay, and both of these are equal to sort of the third picture you could draw where you sort of did it in the other order. So this is one of the axioms of a two category. So the point of all this is that what is a two category? You don't really care, right? You know, the axioms of a two category are just precisely, I mean, really, I should have done if and only if, are just precisely the things that say that a diagram unambiguously, you know, represents a morphism up to rectilinear isotopy. That is, up to taking rectangles and moving them side to side past each other. So long as that makes sense. So, I mean, like, you know, when I write alpha, I'm representing a specific two morphism that I've specified, right? Right, so, I mean, like, this is built up out of building blocks. You've chosen a way to represent alpha as a diagram, you know, a dot labeled alpha, and then any way to glue these diagrams together in some reasonable thing unambiguously represents a kind of composition, right? Just like any way that we draw a couple dots on a line represents a composition of the things that we chose. So let's actually do some examples. So this, like many other tools, is a tool that one gets used to. And one shouldn't stress too much about the abstractness of this, because it's in the end, it's trivial. It's just a tool you have to get used to. Okay. So let's do an example. From last time, we learned about Frobenius extensions. Okay. So we had Frobenius extensions. Okay. We recall that we had functors from A mod to B mod. So A is contained in B. And from B mod back to A mod. This was induction, and this was restriction. Okay? So now I need to choose a way to represent these things by diagrams. Okay? So these are one morphisms. So they should be represented by horizontal line segments. Okay? So I'm going to write A for the category of A modules, and B for the category of B modules. And I'm going to represent induction by, you know, essentially by an upward-oriented point. Okay, this is just a point with an orientation. Okay, you know, maybe I'm stressing that this is a point. It's not actually a line, but in order to draw an orientation on it, you know, I could write a plus sign or something, but I choose to draw a little arrow. Okay, so this is supposed to represent induction, whereas going from B to A by a downwards arrow is supposed to represent restriction. Now, what two morphisms do we have? So remember that along with the Frobenius extension, there were four canonical two morphisms, right? The four units and co-units of a junction. And what were they? So for instance, there was a map from B tensor row over AB, which is, if you recall, is restriction composed of induction, to B. And this map was just multiplication. All right, this is one of our four maps. Well, B is just the identity of B. So how would we draw this? The bottom row is the source. So first we restrict, and then we induce from B to A and back to B. Exactly. The top is the identity of B, so nothing's going on. And I have to draw this diagram somehow. So it's just going to be some symbol, right, molt or something, which connects an upline and a downline and looks like this. All right, so this rectangle here represents some map from this guy to that guy. And I'm just saying this represents, I'm going to use this diagram to represent multiplication. In fact, I'm not even going to draw the dot and write multiplication. I'm actually just going to use the notation that it's this clockwise cap. Okay? And this right here, the B here and an A there, this is going to represent multiplication. Okay? So right now I'm not doing math. I'm just giving you a symbol representing a given thing. Later I'm going to compose these symbols. Okay? But for now I'm just writing down definitionally what they are. Okay? So this is just a definition. This is not math yet. Okay, well, there's a bunch of other maps, right? There was this de Mazur operator from B as an A bimodule to A as an A bimodule. All right, this is just a map from induce restrict, so here's A and there's B, to the identity of A. And this is going to be represented by the counterclockwise cap. Okay, so this is, again, definitionally. I'm going to use delta to represent it this way. And we've got two more maps, and unsurprisingly, they're going to be something else. So we also have the counterclockwise, the clockwise cup. Right, what is this? This is some map from, what's the source? B. And what's the target? So it's restrict and then induce, which is really you just read across the rings, B tensor over A, B. Okay? And what was this map? This was the coproduct. Okay? Whereas we have the fourth map, this one, and now this is a map from A to B, and this was just inclusion. Okay, so we've taken our four canonical maps associated to a Frobenius extension, and we've assigned pictures to them. Now we get to compose these pictures and see what happens. And we'll see that these pictures were a wise choice. Okay? Because by having chosen it this way, things work out nicely. So, what do these satisfy? So, for instance, here's a diagram we can draw. Okay? So what is this in the old language? What have we done? So we have to first compose this, build this out of rectangles. Okay? First decompose it into rectangles to see what is going into it. Okay? So this is some map from induction to induction. Okay, so here's A and here's B. So this is some map from B as a BA bimodule to B as a BA bimodule.
I mean, that's not to say that you're going from A modules to B modules. So you think this one, this last one?
Yes. This thing.
Yeah.
Yeah, so this is B as an A bimodule.
B, okay.
So it's the composition of induction and restriction.
But it is from A mod to A mod.
This is a functor from A mod to A mod, as is this. And this is a natural transformation. These are both functors from A mod to B mod. Right. And it's composed out of a bunch of more elementary pieces. So what this composition does is it takes B, and then it maps it into this triple composition. into B tensor over A, B as an A bimodule. That's what this horizontal line is here. And then it maps that into B. And individually, each of these maps is what? Well, first, we do the identity of B tensored with this map from A to B. So tensored with inclusion. Okay? And then this map is, we do the identity here of B, but then on the first term, on this B tensor over AB, we apply multiplication. Okay? So we do mult tensor the identity. Okay? So when you compose these two things, you're sort of saying, okay, we have an element of B. We then look at an element of B tensor B, but what element? B tensor 1. Okay, so we have an element F, say. It goes to F tensor 1, and then we multiply them. This sends F to F. Okay? So this is the identity map. So this diagram is supposed to be equal to this diagram, which is the identity of B. Okay, so we have this relation here. Okay? Now this is a harder computation. If you do this one, okay, then this computation involves not the identity, the inclusion, and the multiplication, but it involves the trace and the coproduct. Okay? But if you do the same computation, you'll see that you also get the identity map. Okay? That's the way that this is set up. Okay? So these are some relations which hold. And this is the general idea. When you have a complicated diagram, split it into rectangles, analyze the individual rectangles, see what map is actually happening. We'll do many more examples. Okay? So we also have the following relations. Yep.
So I just want to get clear on how to think about this in light of what you said earlier.
Yes.
In the sense that, okay, a rectangle, you think of it is a two-morphism.
Yep.
And this bottom thing is a functor,
Yep.
is a one-morphism.
Yep.
And the top one is a one-morphism.
Yes. So I prefer to, instead of using one morphisms and two morphisms, in this example you can just say the top and the bottom are bimodules, and a rectangle is a bimodule map. If that makes it easier to think about it.
And but a rectangle, what about the vertical sides of the rectangle? What do
The
they
vertical sides are always empty. Nothing happens. That's sort of the notion of generic, right? Remember that we sort of like, in the one category example, when we took a line segment and said that it was a map, we were taking generic line segments. We didn't take line segments that ended in stupid places. So the point is that nothing at all is happening here on the sides. Right, well, same thing. When you take a rectangle, nothing is happening on the sides.
So these sides are generic.
Yeah, these sides are just the identity of some object, right? It's just, yeah, nothing's going on. I mean, because as you see here, this cell really closes up on the right and left. Like, nothing happens. There it comes up. Sure. Okay. So, we have these relations, which, now that we've drawn them in the nice way, basically said that we have not just rectilinear isotopy, but we have curly isotopy, right? We can take a line and curve it around, right? Now, before, in the general context, there was no cups and caps, so it doesn't make sense to rotate something, you know? To rotate something, the picture you end up with has these, like, cups and caps in it. So unless you have cups and caps defined in some way, you can't just take an arbitrary two-category and rotate pictures. But here we have cups and caps defined in a particular way, and we can take a strand and we can bend it around, and the claim is that that doesn't change the morphism. Okay? So Frobenius extensions are a particularly nice example of where these diagrams help because they allow us to use topological intuition to do computations. Okay? You know, there are some more relations, and there's some more morphisms. Okay? So for instance, here's another morphism we could draw. So if we choose an element of A is a commutative ring. then multiplication by that element is an endomorphism of A. So this diagram is supposed to represent the map from A to A, which is multiplication by F. Okay, so now we have a symbol for this as well. Okay, and then you can see various relations like this. So, we have a similar symbol for multiplication by an element of B. And, we'll have something like this, some relation that looks like this. So F is an element of A, which is also an element of B. We're looking at the map from B to B, which is multiplication by F. And it doesn't matter whether you multiply by F here or there. Like, these are going to be the same map. So this is a relation that we have. So there's many more relations that you might find. Okay? What is a clockwise circle? Okay? That's an interesting question. A clockwise circle. Okay, this is a map from B to B. So it's multiplication by any bimodule map from B to B is multiplication by some element of B. Okay? So this is supposed to be equal to multiplication by some element of B. But the question is, what element of B? Okay, so then the question is, where does this send the number 1? Right? Well, what happens is that first we go B to B tensor over AB by co-multiplication. That's this part. And then we multiply. All right, so this sent 1 to this sum over dual bases of BI tensor BI dual. And then we multiply them so we get this sum of BI times BI dual. And that's F. It's a canonical element associated to any Frobenius extension. Okay. So we have relations like this, et cetera, et cetera, et cetera. Right. So the bottom line is the identity, one more transfer over the identity functor of A module. So it's just the bimodule A. And so is the top. And so this is representing some map from A to A. This is a definitional symbol.
So it takes all modules to multiplication by F.
Yes, that's what it does.
The identity is the identity, just multiply by F.
Exactly. That's right. So there's all sorts of relations that you can come up with. In fact, I've written down almost all of them. That are, in fact, you can actually describe the two-category generated by induction and restriction in terms of generators and relations. In fact, every morphism that there is between B tensor over A, B tensor over AB, et cetera, to some other thing of that form, is going to be built out of various cups and caps and multiplication by polynomials. So it's something you can prove. So this actually gives you an entire description of the category in some nice language.
If one never studied two categories but only pictures,
Yeah.
would one lose out or anything?
No. So the answer is yes. The answer is yes, but for a reason I'm going to say in a sec. So I just want to quickly say what is actually going on behind the scenes here. Okay? So I've given you some general nonsense about two categories. Then I gave you this particular example, and in this particular example, things were nice, because there wasn't just rectilinear isotopy, there was true isotopy. Okay? But actually, that is also some general bullshit. So I just wanted to say the general bullshit that underlies that. Okay? So when you have a functor E, and its adjoint, it has a right adjoint. Okay? So maybe E goes from C to D, and the adjoint goes backwards. Okay? Then that means that you have adjunction maps. Right? You have this map from E dual to the identity, and from the identity to E dual E. Let's see. E dual E is, this is the identity of D, and this is the identity of C. So however you represent E, this morphism would be represented as something that looks like this. This is the the unit, and this would be, oh shoot, I'm drawing this one, I'm sorry. This is the co-unit, and this would be a map from E dual, to the identity of D. So it would look like this. Okay? But the point is, if you choose the convention, choose convention that E dual, if E is drawn as an up arrow, labeled by E, then E dual is drawn as a down arrow labeled by E. And eta is drawn as a clockwise cup, and epsilon, this thing here, is drawn as a counterclockwise cup. And if you choose these conventions, then a junction, if you look up what a junction is and what exactly it means, it is exactly the statement that this is equal to that. We can't draw this one yet because we don't have arrows going in that direction. We only have arrows going to the right here. Okay, and also the other thing that you could draw, I think with a down arrow, and the arrows have to go to the right, so they go like this. Okay, so this is a junction. A junction is the existence of two maps satisfying this thing. That is what a junction is. Okay? And if also E dual is left adjoint to E, so if E and E dual are biadjoint, then you have the other cups and caps, the ones that point to the left. And the other relation. Okay? And so in the presence of biadjunction, you can do this whole isotopy business. But there's one thing that might happen. Okay? So suppose that E is biadjoint to E dual, and F is biadjoint to F dual, and beta is some two-morphism from E to F. Okay? So here's beta. Here's E, F, here's beta. Okay? Now, there's two things we can construct out of this and the cups and caps that we know we have for both E and F. Okay? We can do this following thing. Here's beta, going from E to F. And we can apply F's cup here. And we can apply F's cap and E's cup there. And now this is a map from F check to E check. And this is just something that we built out of our basic building blocks. Okay? But there's another thing that we could also do, which is we could have done this one and that one. Okay, and this is another map from F check to E check. Yes, thank you. Thanks very much. Good catch. Okay, so these are two morphisms that we've constructed from F check to E check. And actually, nothing in the axioms of a junction says that these should be the same. So in general, they're not the same. Okay? So if these are actually equal, we say that beta is cyclic with respect to our junctions. Right? So a junction is not a property, it's a structure. It's a choice of these cups and caps. And this is a property of a map, that it's cyclic with respect to these things. That's if this diagram is equal to that diagram. And if so, we might as well take this diagram and just draw it in a different way. You know, if you think about pulling this strand taut, draw both as just a downward pointing B. All right, if we think about pulling this, or maybe I should put the beta upside down. All right, what happens when you pull this, you have this string with a little thing on it, and you pull it like this. Okay? And so if that happens, if something is cyclic, then this represents these two things. And then we can say that isotopy works using those dots as well. That we can pull strands, even strands with dots on them, tight. Okay? And so, you know, there's more complicated situations you might have. You might have 5 functors, and you might have a map from the composition of 3 of them to the composition of 2 of them, and then there's all sorts of curvy things you could draw around, but the notion of cyclicity is still pretty easy to figure out. Okay? So the general nonsense is this. So I want to say this correctly. So if every one morphism has a biojoint, and every 2 morphism is cyclic with respect to these bijunction structures, then the axioms of all this stuff, axioms of bijunction and cyclicity, imply, or maybe are really the same as, the fact that a diagram unambiguously represents a morphism, a 2-morphism, up to true isotopy. Okay, so not just that, you know, boring stuff where we took rectangles and moved them around, but you can take strands and curve them around, and we're really talking about topology now. Okay, so this is the reason. Now, this sort of condition of bijunction and everything being cyclicity, as being cyclic, this seems unnatural, but it's not. Okay, so whenever taking biojoints is functorial, all 2 morphisms are cyclic. So this usually happens in your category as some sort of duality functor. And the dual is an adjoint on both the right and the left. This happens all the time in geometry. This happens all the time in representation theory. This happens for Frobenius extensions in certain contexts. So the point is that whenever there's some sort of duality in your category, so that taking the dual is taking the biojoint, then 2 morphisms are naturally cyclic. And that means that we should be using isotopy classes of diagrams to represent morphisms. So this is the abstract bullshit that underlies this. Okay. Now we actually have to apply this to something useful.
Are there any interesting examples where this condition is not valid?
Yes. So in fact, in Kovanov-Vlada's categorification of the quantum group, actually, it's not cyclic. So in their original thing, they made it cyclic. And it turned out that that doesn't agree with what you get in algebra. So you know, the thing you have to realize is that their categorification of the quantum group is not geometric. Their categorification of the positive half of the quantum group is geometric. But the categorification of the whole thing is not. And so some scalars show up. These 2 things are equal up to a scalar. This is some situation you can deal with, but it's incredibly annoying. Thankfully for us, our situation really is geometric, and we don't have a problem. It's a good question. So that was some abstractness, but again, to get used to it, one just needs to do more examples. Lots and lots and lots and lots of practice. So let's do some practice. So since we're breaking in 10 minutes, I think the practice I choose to do first is, let's just do my original, let's do something not at all abstract, like not a Frobenius extension. Let's do something concrete. So let's do some SL2 representation theory. Okay, so what we're going to do is we're going to choose a monoidal category, which is a two-category with one object. When there's one object, you don't need to bother decorating the, I should have been putting C and D here the whole time, but I wasn't because I'm a jerk. Actually, these are down arrows, so it should be D and C. Right? I should be decorating the regions with the object that we're working in our two category. But if there's only one object, you don't need to decorate the regions. So that's what a monoidal category is. Well, the monoidal category we're going to be looking at is fund, SL2, or just fund, where the objects are tensor products of the standard two-dimensional representation. And the morphisms are SL2 maps. Okay? So we're going to represent V, the standard rep, by just a dot. Okay? We don't have to label the region. There's no region. So that V tensor n is just n dots. Okay? The composition of V in this tensor category. V tensor 0, of course, is no dots, and this is, of course, the identity. This is the trivial representation, which is the monoidal identity. So far, so good. Now let's represent some maps. Okay, so if you remember your representation theory of SL2, you remember that V tensor V is not irreducible anymore. It splits as S2 of V plus lambda 2 of V. So the symmetric part and its exterior part. All right? Now this thing right here is a new irreducible. This is the thing that's usually written as V2. It has highest weight 2. And this thing right here, since we're in SL2, this is just the trivial rep. Okay? So in particular, this guy is not in our category fund. He's not a tensor product of V's. But this guy is. And there's some projection map from here to here. And this is something you can write down explicitly. Okay? So V has basis, let's say, V plus and V minus. Okay? And this is the alternating thing. Right? So this is supposed to be, V plus tensor V minus minus V minus tensor V plus. Okay? So we have this map from V tensor V to C, and this is supposed to be the thing which makes something alternating. So what it does is it takes V plus tensor V plus and V minus tensor V minus to 0. It takes V plus tensor V minus and minus V minus tensor V plus to 1. Okay? We also have our inclusion map, which sends the identity to our alternating guy. I'm going to say V minus tensor V plus V plus tensor V minus. So here are two maps, and you can go and check these are SL2 maps. And you can do this with the quantum group too. You just need to put some Q's in there. Okay? So now we want to find a way to represent these maps. Okay? So we need to represent this as something with two dots on the bottom and nothing on top, and I'm going to represent it like that. Doing this for a reason. By representing it this way, things work out nicely. I'm going to represent this like so. Okay? This one is yes. This should be a minus sign here. So this is the inclusion of the alternating part. Okay? So now we check what relations hold. Yes? Yes. Yeah. V tensor V, exactly. It has nothing to do with V2, just V tensor V. So what, for instance, is a circle? So first off, this is a map from what to what? It's from C to C. So it's just a number. Okay, what number? Well, we said 1, 2, now mapping to V tensor V, to this guy, V minus tensor V plus minus V plus tensor V minus. And then we apply this map, which sends this term to -1 and this term to -1. So we get -2. I chose my scalars, right? I mean, obviously these maps are well defined up to scalar. I could have chosen different scalings, but this is the scaling I've chosen, and with this scaling, a circle is equal to -2. -2 times the empty diagram. Okay? We can take linear combinations of diagrams. This is an additive category. We're allowed to take linear combinations of morphism, so we can take linear combinations of diagrams. This is a linear combination of diagrams. The empty diagram, which is the identity map of C, which is multiplication by 1. Okay? This is a linear combination of diagrams. Okay? So we have this relation that a circle is -2. And then now you can guess from the fact that I drew this as a cup and a cap that maybe there's some isotopy. Okay? So this right here is a map from V to V. Okay? And it sends a vector V to, now it factors through V tensor V tensor V. It sends this vector V to V tensor V minus tensor V plus minus V plus tensor V minus. Okay? And then it applies this map to the first half. Okay, so we need to check what happens. Okay, so I maybe should do this with a little more room. I'm sorry. So V plus is sent to V plus tensor V minus tensor V plus minus V plus tensor V plus tensor V minus. And then we do this to the first two terms. So when we anti-symmetrize this, we get 1 tensor V plus, so we just get V plus. And when we anti-symmetrize this, we get 0. So that term doesn't contribute. So this is just the map that sends V plus to V plus. And if you do the computation, it also sends V minus to V minus. So in fact, it's the identity map. And so this is equal to a straight vertical line. Okay? And again, you can do the computation the other way and get that this is equal to this. Okay. So the result, in fact, this relation and this relation are sufficient to imply all relations. Okay? So the fact, theorem, I think due to Kaufman, or maybe, yeah, I think it's due to Kaufman. So the theorem is that all SL2 maps between V tensor N to V tensor M are monoidally generated, so generated diagrammatically by the cup, the cap and the cup, modulo the relations that a circle is -2 and that you have isotopy. In fact, it's very topological, right? So the answer is you have some sort of one manifold with boundary connecting n dots on the bottom with m dots on the top. And you could have closed parts of this one manifold, but then you can remove them using this relation. Okay, so
Two generators.
exactly, 2 generators, 2 relations, quite simple. Okay. So this is a nice example. And this works for the quantum group as well, actually. For the quantum group, it's minus quantum 2. It's the dimension. It actually has to do with taking the trace and the co-trace. You're taking the dimension of the representation. That's why you get the number 2 showing up. So this is a wonderful application. So this thing that you get is called the temporal, the diagrammatic version has a name. It's called the temporally Lieb category. Okay? So more familiar is the temporally Lieb algebra, which is you fix an n, and you look at the endomorphisms of V tensor n. So that would be things with exactly n dots on the bottom and n dots on the top, and then sort of ways to connect them up. That's an element of the temporally Lieb algebra on 4 strands. Okay, and how do you multiply them? You stack them on top of each other. This is an algebra. Since we fixed the number of dots, we can't stack them side to side. But really, this is just inside the temporally Lieb category. This will be important. And I guess I'll say one thing before we stop for tea, which is that this category fund didn't contain all irreducibles, right? Clearly, we're missing something. Like, so for instance, we don't have V2 as an object. But we could describe V2. V2 is the image of an idempotent endomorphism here. Right? Any summand is the image of the projection to that summand. Okay? Well, what is the projection to this summand? Right? So the identity of V tensor V is equal to the projection to V0 plus the projection to V2. I think we all agree on that. Okay? That's what happens when you have a direct sum decomposition. Well, the identity of V tensor V is this. Okay? The projection to V0 is, well, we apply the projection and then the inclusion. But this isn't quite right, because they're off by a scalar, right? I mean, like, if you square this thing, you get -2 times itself. So actually, maybe we should be dividing by -1/2. That thing right there is this. And the other thing is, well, we don't know it yet. But actually, we just solved for it. Okay? So that says that the projection to V2 is the identity plus 1/2 of that. Okay? And now if we want to understand maps from V2, we just need to apply this idempotent to maps from V tensor V. Okay? So in general, there's this thing called the Jones-Wenzel projector. Both of them basically came up with formulas for this thing. The Jones-Wenzel projector, JWN, lives inside the endomorphism of V tensor n, and its projection to Vn. Okay? And so, you draw this as some sort of, this is JW5, which is some endomorphism from 5 strands to 5 strands. Coming up with a closed formula for this in terms of just cups and caps is very difficult. But there's nice inductive formulas, and this on the exercises. Okay. So these are Jones-Wendell projectors. And when you can compute all these things, then you can recover your original category from this category. And you can always recover it abstractly by just taking all summands. That's a formal abstract notion, like we did yesterday, getting circle bimodules from Bose-Samuelsons. But if you want to be able to do it explicitly and diagrammatically, you've got to actually compute all the idempotents that actually matter. So I think it's good to take a break now. Yes? Yeah. So for the quantum group, if you do the exact same thing and put that there, then this then the statement is true. All UQ-SL2 maps from the standard wrap tensor N to the standard wrap tensor N. But the definition of the cup and cap is slightly different. Like the formula is different. But the presentation of the Hom space by generators and relations is the same. So I'll write down the Jones-Wendell projector on 3 strands. And maybe I switched these two, I forgot. But just to give you an idea that these things aren't easy. Oh, I think I switched them. Yes.
So there also can we actually solve for the idempotent? I mean, of course,
Oh, this is the big question. The answer is no, right? I mean, like this is the question. This is the topic of, yeah, this is the goal, the ultimate goal. Finding these idempotents is the gold standard. They would answer everything for you. So, I mean, like this whole question of characteristic, what happens in finite characteristic, right? You see right here that in characteristic 3, I cannot define this. I can't divide by 3, which means that something weird happens to V tensor V tensor V in characteristic 3. Right? So if you knew which primes divide the denominator, then you know exactly what happens to the representation theory in finite characteristic. So finding these idempotents tells you everything. Just to be nice to you, I just want to start by being very slightly more, just saying it precisely what that theorem was, because there might have been some confusion. So just to sort of differentiate between representation theory and diagrammatics. So the point is that you can define this category, the temporally lead category, where the objects are natural numbers represented as n dots on a line, and the morphisms, so Hom from M to N is supposed to be, has a basis given by sort of one manifold matchings from m dots to n dots with multiplication given by composition modulo those relations. So this is a well-defined category, monoidal category. And then the theorem is that the map from temporally lead category, which is this abstract thing, to fund SL2, which is this concrete representation theorem, representation theoretic thing, is, and this map is defined as by these formulas, is an equivalence. Okay, so that's sort of it's nice to separate in your mind the sort of diagrammatic category from the algebraic one. because we're going to be doing the same thing in a sec. For Zirkel bimodules, we're going to define a diagrammatic category, which doesn't a priori have anything to do with modules, right? Just like this diagrammatic thing has a priori nothing to do with SL2. Okay, and then from that, and then there's going to be a functor, which is an equivalence. I should point out, while I'm erasing, what about SL3, or SL4, or G in general? Okay? So, I mean, one should be able to do the same thing here. And so the reason that there's no orientations on these strands is because V is self-dual for SL2. For SL3, what we're interested in are tensor products of fundamental representations. Now they're not self-dual, they're dual to each other. For SL4, you've got lots of fundamental representations. But this is known in type A. So in type A, there's a theorem just like this one, which gives you some diagrammatic category and a functor to the representation of theoretic one, and it's an equivalence. However, the Jones-Wenzel projectors aren't known. The projections from a tensor product to an indecomposable summit. These are not known. And outside of type A, in rank 2, there's a theorem like this. But for B3, there's nothing. Sorry, for B3, there's nothing.
Sorry, for type A, you always use the fundamental, that is the defining representation.
Yeah, so we're always taking tensor products of fundamental representations.
No, the defining or all fundamental?
All fundamental.
All
All fundamental. Because if you want every representation, you've got to take tensor products of fundamentals.
even the defining one.
You're right. Because they're all the defining ones are yes. But we still take all fundamentals. It's a lot easier that way.
So that means you take all exterior products.
Yes, all exterior powers. Okay, yes. You're absolutely correct. They're all inside the... So for SL3, the reference is, for rank 2, the reference is Cooperberg, Greg Cooperberg. And for SLN higher, it's a very recent paper last year, Kaudas, Kamnitzer, and Wakata. Yes, Kaudas, Kamnitzer, Wakata. So you can ask me later. Okay, so let's do some Zirkel bimodules. Are you ready for it? So let's do Zirkel bimodules in rank 1. Okay, so.
I'm sorry, one more thing. So does the answer get very, very complicated, or is it a nice answer?
It's a nice answer.
It's a nice answer.
It's a very nice answer. Okay, so back to Zirkel bimodules. But really, not Zirkel bimodules, but Bott-Samuelson bimodules. So, I'm not studying all of SL2 representation theory. I'm studying tensor products of fundamental representations. Why? Because if I wanted to write down all morphisms between all irreducibles and tensor products of irreducibles, it gets very difficult. And it involves understanding Jones-Wenzel projectors, and it's actually quite hard. And you can do it for SL2 and for nothing else. So instead, you look at a subcategory, which is easier to understand. And that's exactly what we do here. Instead of Zirkel bimodules, which is what we really care about, we look at Bott-Samuelson bimodules, which is what we can understand. Remember, Bott-Samuelson bimodules are just the things like BS, BT, BS, ... Okay, that was a Bott-Samuelson bimodule. Just some polynomials with walls. So we're going to do the warm-up, which is going to be where there's a single simple reflection. All we can do is just BS, 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 BS. All right. So what do we have? Well, remember, this came from a Frobenius extension. Okay? And there were these 4 canonical maps from a Frobenius extension. And these are going to translate to 4 canonical maps between Bott-Samuelson bimodules. So what are they? So 4 canonical maps. So we have a map from BS to R. This one has played a role. This is the thing. Remember, BS is a wall between 2 polynomials, and we multiply the polynomials. Okay? How are we going to draw it? Well, we're going to draw BS itself as just a dot on a line as usual. Okay? And so we're going to draw this morphism like so. So this is a map from BS to the monoidal identity, which is R. Okay? We also have a map from R to BS. Remember, this is the thing that sent the identity to this natural coproduct element, CS.
How do you decide what the picture is going to be?
I decided. And everyone else must obey my rules. But there's a reason. There's a reason which I'll explain soon. There is a...
I may have drawn a very complicated picture.
Yes. So I'll explain the reason in a second. I mean, certainly it has this boundary and that boundary. So all you can do is just put a symbol here, right? And I chose for that symbol to be a dot. But there is a restriction on what symbols you can choose. I'll explain that in a sec. Okay, anyway, there is a map from R to BS, sending 1 to the unique element for which right and left multiplication is the same. And I'm going to draw that like this. Fair enough. Now, then there's also a map from BS to BS tensor BS. So remember, I'll stop writing the tensor. So BS, remember, is split into 2 copies of BS. Right? And this is the inclusion of one of them. Okay? But more specifically, there's 2 other maps in the Frobenius extension, inclusion and the trace. And this is going to correspond to inclusion. So what you do is inclusion in the middle. So this is going to send 1 tensor 1 to 1 tensor 1 tensor 1. So actually, maybe I'll say it sends F tensor G to F tensor 1 tensor G. It puts a 1 in the middle. This is where inclusion comes into things. Okay? And we're going to draw this like so. It's a map from a single copy of BS to 2 copies of BS. And it's going to look like this, a trivalent vertex. Okay? That's how we're going to draw this. And similarly, we have a map in the other direction. Okay? And what does this do? This is going to correspond to the trace, and it's going to apply in the middle. So given F tensor G tensor H, we apply the trace to G. And we get a symmetric polynomial, something symmetric in S, which means that we can slide it across the wall. It doesn't matter where it goes. So I might as well put it on the left, but it didn't matter where it went. Yes, this is the De Mazur operator. And I'm going to draw this map like a trivalent vertex oriented that way. All right. So, these corresponded to the four canonical maps in a Frobenius representation. In fact, the correspondence is not so bad if we took this and we drew it not in this language of R modules with this monodal category where we don't label any of the regions because there's only one object. If instead we drew it in the way we used to draw it. Okay? And I'll just sort of overlay this for you. This used to be drawn like this. Okay? And this used to be drawn like this. This used to be drawn actually like this. And this used to be drawn like this. Can everyone see those red little things? It's very light.
Maybe you could use a yellow.
Let's see how green is. Yeah, it's much better. This is how it used to be drawn. Okay? So really, we're taking these canonical maps and just putting some other stuff on the side. And then what we do is we use some sort of topological deformation or tract. Okay, so the relations that I'm about to write down are basically going to follow from the relations that we already did for Frobenius extensions, just after you do some stuff and get deformation or tracts. Right? The point, though, I guess maybe I should have said this first, is that BS, which is just a dot on the line, is sent to this new object, which is down up. Right? So the dot becomes a down up because it's restrict induce. in the old language. Okay, so let's write down some relations between these things. Oh, we also have one more generator. I always forget this one. But this is important. There's a map from R to R, which is multiplication by a polynomial. And how do we draw this? We just put the polynomial in a box.
So in this, we have to improve, in this, we have to improve that.
Yes. So let's do an example of computation. Okay? Yes.
When you said this used to be drawn like, the
Yes.
earlier ones, there, however, the tensor product was over RS, here the tensor product is over R.
Yeah. Yeah, well, it's not like really like, there's multiple things. There's induction and restriction. So it's not really tensor product anymore. But yeah, you can think of it as tensor product, yes. But the tensor product is over whatever the region is labeled by. That's how bimodules do things. So let's just do this computation. And after this one, I'm going to then make the rest of the computations exercises. Because they're good ones, because you need practice with this. So what does this map do? Okay? Well, you start with a pair of polynomials, f tensor g. Okay? And then you end up with a triple of polynomials. Okay, okay, so this is supposed to be R bilinear. So we really only need to ask what happens to 1 tensor 1. And that will tell us what happens to f tensor g.
This is again from BS to BS.
This is from BS to BS. But it factors through BS, which is a triple of polynomials. So what we do is we keep the 1 on the left fixed, and then we do this upside-down dot map, which is the thing that sends 1 to CS. What it was CS was, if you recall, alpha s over 2 tensor 1 plus 1 tensor alpha s over 2. Okay? Then we apply this map, which takes the de Mazur operator of the thing in the middle. Okay? So now we get 1 tensor 1 times the de Mazur operator of alpha s over 2 plus 1 tensor alpha s over 2 times the de Mazur operator of 1. Okay? Well, the de Mazur operator of 1 is 0 because 1 is symmetric. So this term dies. The de Mazur operator of alpha s over 2 is 1. That's the whole point. This is why we're doing dual bases. Okay? So this is 1. So the answer is just 1 tensor 1. So in fact, this is the identity map. Okay? So we get a relation that says that this is the identity map. Any questions about that? Do this in more detail. But so this is the kind of computation that you should be able to do. What did I do? I looked at this diagram. The first thing I did was divide it into rectangles. Okay? And that told me what to do in each piece. I did the 1 goes to CS thing, and then I put a 1 on the side, and then I applied that map. Okay. So, you notice that I haven't actually defined any cups or caps yet. Okay, so where is this biadjunction going to come into play? Well, here it is. Okay, so I define the cup this way and the cap this way. And for this to be a biadjunction, you want a relation like this. Okay? So what this actually is, if you write it out, this is some nasty thing that looks like this. Okay? So go home and compute that this is equal to that. Okay? Good. What was the next thing I was going to say? Okay, fair enough. Here's another example computation. This thing right here is called associativity. You might be familiar with that description of associativity. But what does this really say? I mean, you're starting with 4 polynomials, g, h, and k. And what this map does is it takes the Demerzel operator of g, puts it somewhere, then takes the Demerzel operator of h, puts it somewhere. Okay, but since these are symmetric, it doesn't matter where you put it. And since the ring's commutative, it doesn't matter what order you multiply in. So this is just doing it in the other order. Okay?
You just proved that.
So what?
You just proved that.
Yes. But here's some key facts and relations. Okay? Here's an important one. Okay? Okay, I'm not going to prove this. It's an exercise. But here's where I can answer your question. Why did I draw the pictures the way they did? Okay? Well, certainly I can just draw this as anything that I want. It could be a purple dinosaur, okay? I can do that. But this thing then better be, I'll draw the other relation. I've stopped drawing the rectangles. I'm guilty. Okay? So if I draw this thing as a purple dinosaur, I better draw this thing as an upside-down purple dinosaur. Okay? Because this is the whole cyclicity thing. Right? Now, this picture...
No, sorry. Those two sentences. Cyclicity once.
Remember that cyclicity here. Sorry. I'll finish this. There we go. Okay? So here's a morphism. And then I curve this thing. That is the dual, in the sense that I was drawing earlier, this sort of right dual. And this thing right here is the left dual. And cyclicity says that these two things should be equal. And that if they are equal, I can draw them as the upside-down version of what I started with. Okay? So if this is a purple dinosaur, that better be an upside-down purple dinosaur. Okay? Now you'll note that this wasn't quite cyclicity. I took this upward pointing Y shape, and I didn't twist everything around. I twisted just one strand. And I got this one. So the point is, I should have drawn this as some crazy, stupid thing. Could be a purple dinosaur. But whatever I do this is, it better be the purple dinosaur rotated by 120 degrees. Okay? This thing actually has rotational symmetry. If you rotate this by 120 degrees, not by 360. So cyclicity says that if you rotate a picture by 360 degrees, you get what you started with. Okay, but it turns out that for this picture, if you rotate it by 120 degrees, you get what you started with. What do I mean by rotate by 120 degrees? I mean, so here's 360 degrees. So here's 180. Here's 360. Okay, put it all in a big rectangle. And that's rotating something by 360. This is what you started with. That's cyclicity. Okay? Whereas rotation by just 120 is this. Okay, so rotation of this morphism by 120 degrees would be that. But this is actually just equal to itself. So I took this diagram, I rotated it, and I got itself again. So this diagram has 120 degree threefold rotational symmetry, which means that I'm allowed to draw it as something that has threefold rotational symmetry. Okay? If it didn't have that symmetry, it would be a lie to have drawn it that way. Or it would just make the computations much more confusing. So I can use a purple dinosaur so long as this purple dinosaur has 3 wings pointing out like this. Okay? And then this thing better be the purple dinosaur turned on its side. Make sense? Okay? So these pictures and these relations that I've drawn and checked so far are actually all completely general. They hold for any Frobenius algebra. So there's a Frobenius extension, and that says that BS is a Frobenius algebra in the category of R modules. So you can look up what a Frobenius algebra is. But these are all totally general. Then there are some relations that are specific to our case. Okay, so these are general stuff which all follow Frobenius.
I'm sorry, I missed that. What you said, even this 120,
Yes,
that is also a general.
this is all totally general. Yeah. All general stuff from Frobenius algebras. I mean, if you think about it, how would this be drawn in the old picture? In the old picture, this would look like this. Or this would be clockwise. Yeah, it would look like this. But in the old picture, you have isotopy, so that should be the same thing as this. Right? So this is, all of this is really just isotopy, right? This thing right here, maybe this is up, is just rectilinear isotopy. I mean, like, right? So all of these things are really just, you know, isotopy. But now we're going to draw some stuff that isn't. So that's specific to our example. So here, this thing right here, this is a map from R to R, so it's a polynomial. Okay, or it should be a polynomial. Well, what polynomial is it? We take 1 to CS, alpha S over 2 tensor 1 with 1 tensor, and then we multiply it. And so what you actually just get is alpha S. Okay? What about this? All right. What have we done? Why have we done this? We took 1 tensor 1. We got 1 tensor 1 tensor 1. Then we multiply by f, so we get 1 tensor f tensor 1. And then we apply the de Mazur operator, so we get dsf tensor 1. So this is the thing that just multiplies by dsf. And it doesn't matter whether we multiply on the right or the left because it's symmetric. Okay, so when you put f in the eye of the needle, you get dsf coming out. In particular, if this needle were empty, what f is in the eye of the needle? Multiplication by 1. So this is actually 0. What do I mean by 0? It's a linear combination of diagrams. Okay, so 0 times any diagram. Okay, 0 is a linear. I don't have to draw a diagram here, but any diagram will work. Okay, and there's sort of one other specific relation that actually follows from these already, or maybe these follow from that. There's a whole bunch of, you know, a lot of these relations imply each other. So I'll write it down. Actually, I'll just write down the theorem. So remember that S is S. We're just working in one color. Okay. Then these 5 generators generate all R bimodule maps between Bott-Samuelson bimodules modulo the relations. So I'll write down a sort of nice minimal set so that you have them. So we have isotopy once you define the cups and caps like I did earlier. And isotopy also includes cyclicity. Okay, so these are the isotopy relations. You have the sort of some of the Frobenius, the additional Frobenius relations. For instance, the unit and associativity. These are like algebra axioms. And then we have some specific things. Yeah, so that follows from these and isotopy. If we rotate any relation, we'll get another relation. I like to draw isotopy like so, actually. Which is just a rotated version of this. So this is a horizontal line, right? Actually, we're not allowed to have horizontal lines in our pictures. Okay? But you know, up to isotopy, you can represent it by any non-horizontal line, like a cup or a cap, and they're all equal, so it doesn't matter.
So that means whenever you draw a horizontal line, you should interpret it as being through whichever way you
Yeah, I should interpret this as being like that. And now this is a map which makes sense. It's two y's connected by a cap.
But I could have done it.
But you could have done it the other way or anything else, and it doesn't matter because of isotopy.
Right. But the point is, as soon as I take one of those,
Yes.
all other ways are also implied.
That's correct. And then you have the specific relations, which are here. So this double dot here takes 1 tensor 1 to CS. So this is alpha S over 2 plus alpha S over 2. It's a linear combination of diagrams. This is multiplication by CS. It's alpha S over 2 on the left and alpha S over 2 on the right. Then we have the double dot is alpha S, and we have that the needle is 0. And these imply everything else. For instance, this is a consequence. In fact, there's one other important consequence that's good enough that it might as well be a relation. Right, so remember that what we did, if we took F tensor 1, that you can write this as DSF times CS plus 1 tensor SF. This is one of these little formulas that it has to do with this sort of decomposing into symmetric and antisymmetric parts. So in particular, multiplication by F on the left is the same thing as doing this guy and multiplying by DSF plus multiplication by SF on the right. And this is a consequence. And let's see, I have 1 minute left. I've been asked to end at noon. I'm actually a little bit behind what I was hoping to get to today. That's fine. I'll do one other thing. Okay? This diagram here is the identity of BS tensor BS. Okay? But I can use the unit axiom to bring some little dots out here. And then I can take this thing and tilt it 90 degrees and apply that. So I get an alpha S over 2 plus alpha S over 2. Okay? So maybe I'll draw this like this using associativity. I'll just bring the 1/2 out to the outside. This with a double dot plus this with a double dot. This is alpha S, so 1 alpha S over 2, and I turn the H into X. From here to here, so from here to here, I took this relation right here, and I tilted it 90 degrees. So this is the kind of thing you get used to, right? This is why this is an exercise. Okay, but why did I do this? Because each of these are idempotents. Okay? So you think about this as a map from BS to BS. This is one of the projections. And this upper half is one of the inclusions. This is one of the projections, and this is one of the inclusions. I should put the 1/2 somewhere. Like, really, I'll put the 1/2 up there and down here. Okay? So if you think that so that P1 is this, whereas P2 is that. I1 is this, the 1/2, sorry. And I2 is that. Okay? Then then you want to check that that you get an orthogonal system of idempotence. So I1 followed by P1 is this, but this is the identity of BS. Whereas I1 followed by P2 is 0. I2 followed by P2 is 1. I2 followed by P1 is 0. Okay? This basically says that this is an orthogonal system of idempotence. So this is the diagrammatic way of computing that BS is isomorphic to BS plus DS. I suppose I haven't talked about the grading at all yet. But this is a map of, ends up, this is a map of degree -1, and this is the map of degree +1. This is a map of degree +1, that's a map of degree -1, and so that's why there's this. So I'll do the grading next time. Do the grading right now, so it takes no time at all. This is degree +1, +1, -1, -1, and that's the degree of F. Oh, have we proven it? No. I don't intend to, but it's actually quite easy. So I mean, what I would really do is prove the earlier theorem that I didn't state, that for Frobenius extensions, that the diagrams of the curves are everything. And that you can find written down in a paper of mine and Jordy on Frobenius hypercubes. But this is not so hard to prove either.